Good morning again, and sorry for the mistake that happened with this computer in here that apparently kicked you out of the session. Anyway, today we're doing problems from chapter 31. I hope to do them quickly, and I actually did this with another class, so what I can do also, in addition to the recording of this one in here, I'm going to include the link from the other problem session, and hopefully that will cover everything for this chapter, okay? Then the other thing also, we still have chapter 32 that is needed. Chapter 32 is big, okay, with its applications also, which has tremendous impact in terms of the exam. So we have full sessions this week. Most likely we will cover everything by the end of the week. So this is what we're going to do. Meeting today for 31 problems and hopefully start 32. We'll finish 32 hopefully by Thursday morning, and maybe actually start the problems from chapter 32. Then we will finish the problems in the evening on that very same day. The reason why I'm doing that is because I want to give you enough time to prepare for the second midterm, which is going to be next week on Thursday. And then also, so there will be no class next Tuesday. There will be no class after this week at all. There will be nothing other than this week. So we're going to finish everything. And then also we'll have the final the week after. So at this point, everything looks like we're going to be on campus for the final, but watch for the changes, because they may not want us to come into campus and do that anymore. Okay, I will let you know, guys, what's going on. So that is basically in terms of the course overall. So let me jump into my OneNote. Share OneNote. Okay. So according to this one in here, let me find this one. So the problems we're going to be doing from chapter 31 are the following. Problem 37, 38, 39, and you guessed it, problem 40 also part of the same thing. Okay. So these are the four problems, and you can guess what this thing is. It's emphasizing on the RLC circuits, okay? Part of it, which is really the main topic. So problem 37 basically says the following. You have a coil, has a resistance R equals to 48 ohms. Please pay attention to the sig figs. This actually says 48.0 ohms. That means there are 3 sig figs in this problem. At a frequency of 80 hertz, 80.0 hertz. So the frequency is 80.0 hertz. Okay. And then it says the voltage across the coil leads the current by 52.3 degrees. So phi is equal to, I'm going to leave it in here blank, 52.3 degrees. The reason why I'm leaving in the blank, because I need to deduce from the language which one is ahead and which one is leading. Based on that, I'm going to determine the sign of phi. Is it positive or is it negative? In other words, I need to determine what sign I should use in here. The fact that there is a phase difference of 52.3 degrees is just a phase difference. Which sign should I put in here? That is the question. Determine the inductance of the coil. So the question says in here, and you have to pay attention to the verbiage, it's very important. The voltage across the coil leads the current. So the voltage across the coil, here's the current, whatever it is, and here is the voltage across the coil. And it leads it by an amount that is 50. So this is the voltage across the resistor, which is equal to Ri. So when they tell you the current, they mean VR. So this is the voltage across the resistor, and this is the voltage across the inductor, and that voltage is 52.3 degrees. Obviously, in this case, it's a positive value, so that is why I'm going to use a positive value in here. In other words, the frequency is too high, and the circuit is actually inductive. Meaning, when I look at phi, which is the arctangent of XL minus XC over R, and XL is omega L, and this one is 1 over omega C, this one is bigger than the other one, okay? Because omega L times I is more than 1 over omega C, which makes this whole thing omega L times I is ahead even of the current, let alone of the voltage. So that's why the value in here needs to be positive. So this is how you analyze problems, just by looking at the verbiage, and you determine things in here. Now from here, you're supposed to find, what is the question? Determine the inductance of the coil. Okay. We know there is no capacitance. So as a matter of fact, XC is equal to 0. Okay. So this must be positive anyway. So that means that phi is arc tangent of omega L over R, or if you wish, omega L over R is equal to tangent of phi. And from here, I'm going to find that L is R over omega times tangent of phi. And that's in a nutshell what the answer to the problem is. However, they didn't give us omega, they gave us F. So please pay attention to this little detail that omega and F are related to one another through this expression. Since we know what F is, then we know that this is 2 pi times 80. So the answer here is 160 pi. So the inductance then in this case is going to be R, and R is given to be 48 ohms divided by 160 pi, and that is in radians per second, of course. And the answer is going to be in Henry times the tangent, of 52.3 degrees. Okay, so let's plug in everything in here and see what we have in the calculator. How about this? Check, find the answer. You have everything in here. 48 over 160 pi times tangent of 52 degrees. Can you do that, guys?
Shouldn't be a problem.
Okay, this is problem 1, straightforward. Okay. Problem 2, which is problem 38 in the book. It gives you in an LRC series circuit, the phase phi is 53 degrees. So this is problem 58. 58, yes. No, 38, what am I talking about? 38. So it gives you from the get-go phi is equal to, again, I don't know what it is, 53 degrees, 53.0 degrees to be more specific, okay? The mistake that you make in this kind of problems, again, is the mode of the calculator. It needs to be in the proper mode. So if you're using degrees, make sure it's in degrees. So if it is in radians and you're given angles in degrees, make sure you convert it back into degrees. Otherwise, you'll get wrong answers everywhere, okay? And the source voltage. So now here is what the says in here. The phase angle is 53 degrees and the source voltage lags the current. Here is a current. Here is your L. Here's your C. Okay. So this is omega 1 over omega C times I, if you wish. This is omega L times I, and this is your R omega. Here, they tell you that it lags it by 53 degrees. This is 53 degrees, actually. The voltage across everything else is behind the current by 53 degrees. So the correct sign in here is a negative sign. The other one is ahead. This one is behind. So this is why it's very important to read the verbiage in here, since it says it lags the current. The voltage lags the current. If they said it backward, if they said the current lags the voltage, then it's going to be positive. If the voltage lags behind the current, then it's negative. If the voltage is ahead of the current, it's positive. If the voltage is behind the current, then it's negative. So that is basically the verbiage in here. You have to pay attention to these words here. So now it's a negative sign, actually. That means the capacitance in here is bigger than the inductor. So this is actually more of a capacitive circuit. In other words, this guy is winning. Okay, that's what made this whole thing negative. Having said that, the resistance is 300 ohms, so they gave us R. 300 ohms. Okay. And the reactance of the capacitor is XC is 500 ohms. Since it is 500 ohms, no matter what happened, I need to find XL to be less than 500. This is the consequence of the fact that that's negative. So no matter what I find for XL, it better be less than 500 because this lags by negative value. So this XC, which is this amount, is bigger than XL. So this number for XL must be less than this one here, since they gave us XC. What is the reactance of the inductor? Well, it's easy then in this case. I know tangent of phi is equal to XL minus XC over R. And since I don't know what this number is, I'm going to solve for it. So this is actually XL over R minus XC over CR. Move this to the other side and multiply by R everywhere to find XL. So this is a simple algebra that gives me XL equals to XC, when I multiply by R, is going to give me plus R tangent of phi. It doesn't look like it, does it? It doesn't look like this. XL is less than XC, but don't forget that phi is negative. So the tangent in here better account for that. So here is the answer. XL is going to be 500 ohms minus 300 ohms, or if you wish, tangent of minus 53 degrees. If you do that, the number should be less because of this negative sign in here. So I use this formula exactly how it is. So let's see, where's my calculator? And the answer better be less, okay? So make sure you get the same answer in here. So I have 500 plus tangent, plus 300 times tangent of negative 53 degrees. And the answer is 101.88, which is XL makes it 102 ohms. It is less than 500. That's the point that I'm trying to argue in here. Because the whole circuit is capacitive, meaning that the capacitance is winning. Since it's 500 ohms, then I better find XL to be less than 500, period. End of the story, no matter what I find, even if it's 499. Okay, but if it's 499, this angle will be very, very small angle. Because the difference between 500 and 499 is a very tiny number. It's going to be this much. So the angle should be very close from zero. But since it's very high, 53 degrees is a very high angle, more than the median, more than 45 degrees. Actually, the 53 degrees is here somewhere. It's more than 45. So that in this case, it's a big difference, like day and night. 500 ohms versus 102 ohms is big difference. Does this make sense to you guys?
Yes, it does.
Yes.
Very good. Okay, very good. So as long as you're following, you're in good shape then. Okay, very good. So the average power delivered by the source, well, they gave us also the average power. Forgot about that. They give us P on average. I'm going to give it a leg because of something I'm anticipating down the road. So this is the power. So the power has a leg underneath, okay? Has a foot. So they gave us that to be 80 watts. Don't forget that I put the bar on top just to indicate that it's an average, okay? What is the current amplitude in the circuit, okay? Since they gave us the average power, and we know that the average power is given by basically R times I RMS squared, okay? And I RMS squared is just basically I RMS is equal to I naught, which is the biggest value divided by square root of 2. This is the actual max value or the amplitude. So this is the amplitude divided by square root of 2. So that means that this value is equal to 1/2 of R I naught squared. Since we have the power and we have R, we're going to find what I naught is. So I naught should be, this is the amplitude of the current, basically square root of 2p average divided by r. And that is square root of 160 divided by r, which is 300 ohms. Square root of 16 divided by 300, or 4 divided by square root of 300. 16 divided by 300, enter the 330. I already canceled the 0 in there. It's 0.3 amps, 0.73 amps. 0 to be more specific if you want to include the next number, okay? So this is the maximum value or the amplitude of the current. This is not the effective value. The effective value you have to divide by the square root of 2. Okay? And what's the next question is? What is the voltage amplitude of the source? Well, in this case, we have everything to find that voltage amplitude. Remember, V amplitude is equal to Z times I amplitude, where Z is equal to square root of R squared plus XL minus XC squared. Okay? That is the formula for Z, and we just found I naught. So all we have to do is just find Z, and we're in business. So Z is equal to square root of 300 squared plus 500 minus 102, not 120 squared. So if I plug in everything in here, I will find the value for Z and multiply it by the current, and we are in business. So it's going to be, if the current, first of all, is 0.730, I took the whole value, so it might be different than what you guys find, times the square root of, open parentheses, 300 squared. That's the resistance, plus, open parentheses, 500 minus 102. The whole thing is squared, and the whole thing is under the square root. So that gave me 363.98 or 364 volts. So V naught already is equal to, because I plugged in this value in here for I naught. So 364 volts. Okay. It's just following basically the formulas that we developed in class. I know it looked messy and ugly when we did it in the class and all of that, but if you try to decipher these relations, this is how they look like, basically. Much, much easier than the lecture. So when we do these problems, okay, it's easier to follow at least. Make sense?
Yes.
Sir.
Okay. Very good. So let me get into a problem. The next problem is 39, and then the last one is 40. So let's do 39. Problem 39, it says an LRC circuit, and I call them RLC, okay, because I get used to that. Has a C, so this is 39. C, they give you a C to be 4.80 microfarads, okay, that's fine. And they give you L to be 0.520 Henry, okay? And the source voltage, V, equal to 56 volts. So when they say this one, what they mean by it, it's the amplitude of the voltage. The voltage is an AC source, okay? It's not a DC source. The source is operated at the frequency of the circuit. So they gave you even the frequency. The frequency of the circuit, if you remember, is F naught. So F is equal to F naught, where omega naught is equal to 1 over square root of LC. That, and F naught and omega naught are related through this similar relationship. So that means that omega of the signal is actually equal to omega naught. Okay, and LC, we know what LC is, and then square it. So the omega of the signal is the same as the omega naught, which is 1 over the square root of these two numbers. So I have to multiply 4.8 times 10 to the negative 6 times 0.520, if you like. That's fine. This is decimal point, under the square root. So I need to find this frequency in here, or angular frequency in this case. So it's going to be 1 over square root of, open parentheses, of 4.8, 10 to the negative 6 times 0.52. So this frequency is, or angular frequency is, I should invert it. I forgot to divide by this number. Okay, let me do it again because I think I entered it wrong. It's 1 over and then square root of, because I found a very small number. Usually the frequency is a very high number, okay? So if you find a very tiny number, that means there is something issue in there that in your calculation. So that pay attention to this little detail, please. 4.8 times 10 to the negative, because look at 10 to the negative 6 as the denominator, albeit when you square it, it's going to be 10 to the negative 3, but when you take it up, it's going to be 1,000 divided by square root of 4.8 times 0.5, which is square root of 2. So 1 over square root of 2 basically times 1,000. So it's going to be a big number, probably anywhere between 100 to 1,000. So the fact that I found 0.0173, I know it's wrong because I forgot to divide by it. Or at least when I was typing, I tapped 2 past 30. So 0.52. So pay attention to this little detail. So what's telling me in here is this number is actually 633 radians per second, okay? 632.96, so I rounded everything up to 633 radians per second. So we know the frequency of the signal, okay, which is the same natural frequency of the circuit, okay? So we are at resonance, in other words. We are really at that point when the amplitude, when the phase changes. This is negative 90 degrees, this is positive 90 degrees, and in here, at omega naught, the signal changes. So the phase in here is equal to 0 at this point. And the signal is peaked, actually, around the peak frequency, not exactly peaked. So this is the current I as a function of omega, and this is omega naught. Anyway, that's what this thing is saying in here. If the voltage across if the voltage across the capacitor has an amplitude, so VL, no, not VL, VC. The capacitor is 80.0 volts, which is equal omega, I'm sorry, which is equal I naught over omega C. That is what that number is, okay? What is the value of R? So we need to find I naught from this expression. Once we find the value of I naught, we know we are at resonance, okay? Since we know we are at resonance, the voltage across the inductor then is also the same thing. This should be equal to omega L times I naught, because VC and VL at that point, they cancel. So the entire thing for the circuit will give me the entire V, which is 56 volts, must be equal to Z times I naught. But Z in this case is equal to square root of R squared plus XL minus XC squared and the square root. And this number is 0 at resonance. This number is 0 because on one side it's omega L, and the other side it's 1 over omega C. And both of these two numbers are equal to one another because L and C are, we are at resonance, and resonance is exactly when omega is equal to 1 over square root of LC. So these two numbers are identical. So in this case, Z is equal to R. At resonance, Z is equal to R, end of the story. Here, the impedance is equal to R. In anywhere else, it's always equal to the square root of R squared plus XL minus XC squared. In this section in here, XL is greater than XC. In this section in here, XC is greater than XL. In here, they're equal to one another at resonance. So now I need to find I naught. I can find it from this expression or this expression, it doesn't matter. Both of them are the same. Both of them are going to give me the same thing. In other words, check, please, that I naught is equal to VC, which is given to be 80 volts. Let me do the algebra first. It's VC divided by omega L using this expression, or it's VC, the same voltage actually, times omega c. So you do the algebra, both of them should give you the same number. In other words, I have 80 divided by, we find omega to be 633 times L 0.52, which should be the same thing as 80. Why do I have to do multiplication? 80 times 633 times 4.8 times 10 to the negative 6. I need you to verify that this statement is accurate, that these two measurements will give you the same number, because the voltages, they must be giving the same thing. Both of them are 80 volts. So let me check this one with you guys, because it's an important point that I want you guys to be at ease with. So the first one says divide 80 by, open parentheses, 630. Remember, 633 is a rounded number, okay? So it's going to be almost equal because of the rounding. So this is giving me 0.243 amps. So this one is giving me 0.243 amps with some stuff that is at the end. If I do the same thing now, 80 times 633 times 4.8 times 10 to the negative 6. This is, as you can clearly see, up to the next digit after the rounding, they're the same number. That's the fourth digit that is different. Does this make sense to you guys?
Yeah.
Okay, very good. So the point I'm trying to say in here, at resonance, the two voltages are the same voltage. Therefore, I could use this expression or that expression, I find the same current. This is amps, and that is amps. But they didn't ask me that. They asked me for the volt, what is the value of R? Since I know what the overall value of the voltage, 56 volts, the overall voltage is 56 volts, they gave me this. This must be equal to R times I naught, and this is V naught, by the way. And from here, I find that R is equal to V naught over I naught, which is 56 divided by this value of 2.243. So it's going to be some value in here, which I can do quickly. 56 divided by 0.243. And the value turned out to be 230 ohms. Okay, so we have the resistance now, since they didn't give us a resistance. I want you guys to come back to these problems and study them carefully, okay? I want you to really be at ease with them. The last problem of the series in here that we're planning on doing together, they gave us this circuit. Let me draw the circuit for you. First of all, we have an RLC circuit. We have a resistor. We have an inductor. And we have a capacitor. And at the end, we have a power source. Technically, we should really have and this power source has an alternating current. And technically, we should have a switch, really. But that's another thing, okay? So they give us the values that they have, okay? So they have R equals to 200 ohms. They have L equals to 0.4 Henry. They have C equals to 6 microfarads. Okay, but they draw points A here and B here, and they have the point C in here and the point D in here, and they put ideal voltmeters across them. So there is a voltmeter in here, man, V1, okay? There is an ideal voltmeter V2 here. There is an ideal voltmeter in here, V3. There is an ideal voltmeter in here, V4, between points C and B, I'm sorry. And the last one is an ideal voltmeter overall. V5 in here between all of them. And the question in here is, they give you the values of C. They give you also omega, two values of omega. They give you the V in here for the entire power source. So this V in here is reading 30 volts from the power source, and the omega of the power source, two values. You have to consider 200 radians per second, and you have to consider another frequency that is 1,000 radians per second. The obvious thing that we do in this case is to see where the resonance is. So let's find omega naught. Omega naught is 1 over square root of LC in here. That is something that is obvious in here. So it's going to be 1 over square root of 0.4 times 6 times 10 to the negative 6. Let's find where that omega C. In other words, it's probably sitting in the middle. And if it is, then probably we have different circuits. At some point, for high frequencies, the circuit is going to be inductive. For low frequencies, the circuit is going to be capacitive. So let's see that. First of all, I need to find that 1 over, let's not do the same mistake as before, square root of, open parentheses, of 0.4 times 6 times 10 to the negative 6. And close the parentheses and do the algebra. It's 645.4.449. So it's 0.4. So this frequency is 644.5 radians per second. And that is sitting in here, somewhere in the middle. It's indeed, this is the natural frequency of the circuit. Since this is higher than it, this is higher than omega naught, then indeed, in here, omega L wins. In other words, XL wins. So the circuit in this case for 1,000 radians per second is going to be inductive. And phi is going to be positive. For this case in here, omega 1 over omega C will win. In other words, XC will win. So in this case, it's going to be capacitive. And in this case, phi will be negative. In here, at 645, if they gave us to 645, we will find phi exactly equal to 0. Neither win. And at that point, it's actually the resistance is the one that Z equal to R at this point for 645. And here, Z is equal to square root of R squared plus XL minus XC squared, and same thing in here, okay? So since they gave us two frequencies, let's find these numbers in here. So the first one in here is, what is the reading of each voltmeter? That's the question. For part A, part B. Part A is omega is equal to 200, part B is 1,000. So I'm going to leave it with the omega and find them. So the first one, the reading across this one in here, I need to find I naught. If I don't have I naught, I can't find what V1 is, because V1 is going to be R times I naught. So I need to find I naught. So I naught, I need to find Z for I naught. So I know overall V. Oh, there is a question in here that you have to remember in here. They're calibrated, the voltmeters are calibrated to read the RMS. They are not calibrated to read the amplitude. Since they gave me the amplitude 30 volt, I need to find the RMS. The RMS is going to be equal to 30 divided by square root of 2. So the actual RMS is going to be 30 divided by square root of 2. And that number is 21.2 volts. And that is V5 actually. V5 is going to read 21.2 volts. Because it's across everybody. It's the same thing in here. So that number is not different than this one. It's the same thing. I need to find I naught to do things. But I cannot use I naught now because I really want to find V1 in RMS. So I need to find I RMS. So this becomes R times I RMS. Okay? Not this expression I should, because this doesn't read the actual amplitude. It reads the root mean squared. So what I need to do in this case is find the I RMS. It's the same thing as the V RMS divided by Z. And Z is equal to the square root of R squared plus omega L minus 1 over omega C squared. Obviously, this expression depends on omega. So we'll have two values for Z. I will have Z1 or Z for 200, which is equal to square root of R squared, and R squared, they gave you the value for it. R squared is 200 squared plus, now omega is equal to 200, so it's going to be 200 times L, and L is 0.4 minus 1 over 200 times, that is the omega now, times the frequency, and the frequency is 6 times 10 to the negative 6, and this whole thing square under the square root. In the same time, I'm going to find Z1000, and Z1000 is going to be square root of R squared, which is still 200, plus I have now 1000 times 0.4 minus 1 over 1000 times 6 times 10 to the negative 6, and the whole squared under the square root. So you guys see that I'm going to find two different values for Z, depending on the frequency. Yes? Sounds good? Because I have plugged in the value of omega here of 200, and I plugged in the value of omega in here at 1000. Depending on that, I'm going to find two values for Z. Then I will find two values of the I. So I RMS. So let's find what these two Z's are. So this value in here and this value in here. So I'm going to find the square root of. I'm trusting that you guys will do these numbers on your own, okay? So don't rely on this calculator in here. Plus open parentheses. So I'm going to plug in 200 times 0.4 minus 1 over open parentheses 200 times 6 times 10 to the negative 6. Close the parentheses, close the second parenthesis, square that parentheses, and close the entire parentheses for the square root. So this is the first value of Z. This one is 779.4 ohms. The unit for the impedance is ohms. Now I need to take the same expression and change the 200, the second 200, because the first one is part of the resistance, to 1000. And the last one also to 1000. And this gives me 307 ohms. So obviously the IRMS depends on these two values. So IRMS now, I have two values. I have, first of all, the expression is going to be still VRMS divided by Z, and I have two values for Z. So this is going to be equal to, and VRMS is 21.2. So it's going to be, let me pick up this number in here and divide by the first one for the 700. Come on. So the first current is 0.0272 amps. And the second current is, where is the expression here? So the same current from before, the same voltage, I'm sorry. Come on. Divided by the second resistance, and that's of course a higher current because the impedance is less in this case. So it's 0.0690 amps, okay? So that is the two currents, but I need to find now what V1 is. V1 then in the two readings are going to be, basically it's always R times IRMS. So it's going to be 200 times this number and 200 times the other number. So it's going to be 200, because this resistance is 200. So it's going to be 200 times the first current. And the answer is 5.44 volts. And the second value is going to be 200 times why can't I do this? Okay, let me do it manually. 200 times 0.069, and that's the end of it. 13.8 volts. Does this make sense so far? And then, of course, you're going to find the two values for V2. V2 also is going to be equal to V2 is equal to going to be omega L times I2. And omega now differs, okay? So it's going to be 200 times L, and L is given to be equal to 0.4 times the first current, and the first current is 0.0272 amps, and the second value is going to be 1,000 times 0.4 times 0.069. Okay, so this is, and the same thing I'm going to assume that you guys can do for V3, the voltage across the capacitor is going to be equal to not I2, IRMS divided by omega C, and that 2 is equal to 0.0272 divided by 200 times 6 times 10 to the negative 6, and this is going to be 0.069 divided by 1,000 times 6 times 10 to the negative 6. So these are the two values. So I'm leaving it for you guys to finish the algebra in here, to finish the numbers in here. Finally, I need to find V4. V4 is going to be equal to the absolute value, because it's going to be sometimes positive, sometimes negative. Since it's the RMS, it's always going to be positive. So it's going to be VL, not VL, V4. This is V4. It's going to be VL minus VC. Obviously, it's going to be two different numbers. And VL is actually V2, and VC is going to be V3. So it's going to be the absolute value difference between V2 minus V3. In other words, take this number, deduct from it this number, that's one reading. Take this number, deduct from it this number, and that's going to be the second reading, and both of them are going to be positive. RMS is always positive. This is an RMS value. All of them are RMS values. RMS, and even the amplitude, both of them are actually positive. That's why sometimes the voltage across the capacitor is winning, and the value will be negative if I do it this way, okay? So it's always the difference in absolute value. And finally, that's V4. We did all of them. So I want you guys to come back into this one in here and do it in detail if you really have any doubts about it. Does this make sense to you? Yes, no?
Yes, it does make sense.
Beautiful.
Yes.
Okay, very good. Listen, guys, this is important for your exam, okay? So I'm going to stop sharing this thing here and talk a little bit more about the chapter 32 now, because those are the problems I planned for you guys, similar to the other class too. And I have the recording actually on the other class on YouTube. So if you choose to, you can go there so that you can see if there are things that you probably learn from the other one or more than this one, or vice versa. And I said that to them too. Okay. So let's take stock of where we are right now. This is chapter 32. Chapter 32 is going to be everything that we learned up to this point. Chapter 32 really takes all of the equations that we learn and solve them. But before solving them, there is something the matter with the Ampere's law, and we need to fix that. It was actually Maxwell who recognized that, and he fixed it. When he fixed it, the law became known now. It's known as Ampere Maxwell's law, because he had to fix it. So when we met the first time around was on what is it, February 17th, when we first met on this class. When we first met, then we basically at that point went through Coulomb's law. I asked the question, I don't know if you guys remember it or not. Let me share the screen to take these things into perspective in here, share. We're going to jump into 32 anyway. So when we first met, I asked, what did you guys learn from physics 4a? And physics 4a, basically the biggest deal that you learned is F equals to ma, albeit these are vectors. So this is really the biggest thing that you should retain from physics 4a. So this is physics 4a. By the way, I'm going to tell you about today. Today is the day of the 3 Ps. Okay? There will be 3 Ps in this lecture, in this chapter. The first P is the power. And the power is, we discovered it several times, I guess. It's a force times velocity. It's the rate of work divided by time, the rate at which work is done by time, or it's actually the current times voltage. It's all kind of these things. It's the same concept. It's in watts. So the power, I'm giving it a leg, foot, if you wish, okay, to distinguish it from something else, from another P that you guys also saw in physics 4A, and that is the momentum. So the momentum also uses the letter P, so I'm giving it a ponytail, if you wish, okay? So this is the momentum. Just to make a distinction between the two P's so that you guys don't get confused between the two. At the end of the day, this one is probably not going to be remembered much, but it's going to be needed actually for some of the problems we'll be doing, because we need to find forces and things with it. And the force is the rate at which the momentum is changing with time. So the momentum is actually needed for this chapter. So this is the second P. The third P that we're going to need, and it's going to be tremendous for your problems and for your exam and everything else, is with no foot and no ponytail. It's just a regular P. And this is going to be the pressure. Unfortunately, that's how it comes out. I mean, this concept, they have the same symbol, but I'm just trying to help you out in here, trying to give you a different distinction with them. You should know them in the context. Actually, if you do dimensional analysis, you should know that the power is in watts, or if you wish, it's in joule per second. It's the same thing. The momentum is actually going to be force times second, which is in Newton second, or alternatively, it's velocity times mass, kilogram meter per second, except it doesn't make sense to talk about it in terms of kilogram meter per second in this context, because there is no mass. Electromagnetic radiation does not have a mass. So it's better to talk about it in terms of force times the time, which is the units for the impulse. This stuff is from physics 4A. And the pressure is actually the force divided by area, which is a Newton per meter squared. So this is the stuff that we will need in this class. So this is the day of the 3 Ps, or the chapter of the 3 Ps. That's one thing. The other thing also that you will notice in this chapter, we're doing physics 4B. So it's all about physics 4B. I just started with physics 4A. There are things that we cover in physics 4C that we will need at some point in this class. There are things actually you will cover down the road in physics 4D that we will need. So this is also the day where all the physics is also, or the chapter where all of the physics sequence is needed, okay? So, and the other thing about this what's so special about this chapter is it summarizes everything we learned in this class, okay? So it's kind of a climax, if you wish, for the entire concept that are covered in this class. So the chapter is really about solving Maxwell's equations. So let's start with what we started. So we know F equals to ma, and when we started with this, we're going to discover a new force, and this force is the electrostatic force. At the end, we resolve it to this form for it, which is F equals to QE. If I have an electric field, all I have to do is multiply the charge by it. That gives me the electrostatic component of it, or the electric component of it, plus QV. If this charge happens to be moving in a magnetic field, it's also going to be subject to this force. So this is the electromagnetic force, the EM force. And this is Lorentz force, actually, or Lorentz formula. Now, if I know what E is and what B is, the promise is that I can go back into this equation and find the acceleration. It turns out that's not really relevant. It turns out that actually E and B by themselves have tremendous value in them, and they lead to a lot of physics, and that's what we're discovering in this class. One of them is, for example, E derives from a potential, and from there we were able to find circuits and do AC circuits, DC circuits, resistors, parallel series. We found a lot of things with that thing. So that is just from here, from this concept in here. There is actually another potential for the magnetic field. It's called the vector potential. The magnetic vector potential, I'm not going to be introducing it in this level because it's a little bit more complicated, but it doesn't really bring at least a lot of physics at this point. So I'm not going to introduce it. It brings some symmetry in the math, and that is nice, but not needed at this point. But if we find E and B, we're in business. So let's see if we can find them for a general case, and that case is in free space. Before I do that, let me write Maxwell's equations that we learned. E, which turns out, derives from a charge. I mean, it's produced by charge distribution of some sort. Gauss's law, if you guys remember, says the following: the flux of the electric field over a closed surface is equal to the charge enclosed divided by epsilon naught. The flux is actually an integral over an area, and that integral better be closed. So this is EDA is equal to the charge enclosed. It's basically the sum of all of the charges. So I have a distribution charge in here, rho. That means I have to integrate through the entire volume enclosed by the same surface, divided by epsilon naught. So this is basically what this law is written. Now, if I apply Gauss's theorem in mathematics, this double integral over this closed path, I can convert it into a triple integral over the same volume as this one, where now instead of integrating over EDA, of course, I'm going to integrate over volume, and the value in that case is going to be the divergence of the electric field, which means that since this boundaries of integration, namely the volume, is arbitrary, then the integrand must be true. So there is a math basically step in here to go step by step using Gauss's theorem to convert this expression into the divergence of the electric field is equal to the integrand in this case, which is rho, divided by epsilon naught. So these two are equivalent. As a matter of fact, I can go from this one to the other one mathematically. This requires a little bit of vector calculus, as you're going to see down the road in vector calculus from Calc 3 or Calc 4 or something else. So at this point, take my word for it, okay, that this is true statement. So in other words, I know how the electric field diverges. So this tells me how the electric field flows. So we know how the story is, and it's this value, basically. Okay, that's good. Then we also, when we introduced the magnetic field, we do something similar, and we said that the flux of the magnetic field over any closed surface must be zero no matter what, and that is because there are no monopoles. So if you wish, this is the equivalent of Gauss's law. I mean, Gauss's law for the magnetic field, but the fact that I don't have any monopoles, so I can leave any point in here and come back to it. It's always a circle. So no matter what surface I take in here, it's going to have an incoming field lines and an outgoing field lines that count exactly and cancel. Since the measure of the flux over any closed surface is really nothing but the counting of the number of field lines in and out. Since both of them, they match, since they come in pairs, it doesn't matter where the magnet is. Is going to cancel of all of the field lines. So that is basically the second thing that we learn. In other words, if I apply Gauss's theorem again to this expression, this amounts to saying that the magnetic field does not diverge, that the magnetic field always circulates. So this is also the same thing. It's always zero. The reason why it's not zero in here, because you can isolate positive charges by themselves and negative charges by themselves, and you can count them individually. And at the end of the day, you might end up with a positive sum or a negative sum. So what this theorem is telling you is the net field lines, if it is positive, it's actually an outflow of field lines of the electric field. If it's a negative, it's an inflow, an influx of the field lines. That's all there is to it. If it's zero, there is no influx and outflux. They cancel each other, and that's the end of it. But in here, no matter how you do it, there is no way for you to have a net outflux, if you wish, or outflow of field lines, or net of an influence. They're always going to cancel, no matter how you do it. So in this case, it tells me that basically the magnetic field does not flow. Period. So now I have knowledge of how these two vectors flow. One of them, I know how it flows actually outward or inward, depending on the charges enclosed, and the other one never flows. It's always going in circles. As a matter of fact, we need the circulation for the magnetic field, okay? But before I do the circulation for the magnetic field, let's find the circulation for the electric field. By Faraday-Lenz law, what we found there is that actually there is an EMF, which is really the circulation of the electric field. So we found the EMF to be equal to minus, that's what the contribution of Mr. Lenz is, the derivative of the flux of the magnetic field over where we are looking to find this EMF. So imagine I have a loop, then I can find the electric field and its circulation in that loop. This is what the EMF is, okay? Is equal to minus the derivative with respect to time of the flux of the magnetic field in that region of space too. Okay, so I can convert this single integral, which is actually closed the path integral, and the path integral is actually surrounding that same area in here. So in other words, if I take a path in here like this, then this is the area that is sustained by that path. Or I can blow on it and make it bigger, and it's going to be like this shape in here. As long as it's an area, it's the same thing. It's a different area that is enclosed by the same path. So as long as I take any area that is enclosed by that same path, this theorem works. There is a Stokes theorem that converts this path integral into actually a double integral over the same area, and that becomes the integral of the curl of the electric field. And the curl of the electric field, and again, this is vector calculus, which I'm not going to get into, but I'm hoping that you guys, by the way, the derivation for this one is not really hard when you do Calc 3 or 4, I don't remember what it is. But if you want more detail and physical insight to it, there is actually a Feynman lectures, which gives, and I know I included it in my syllabus, where it really gives a very simple, intuitive, and actually very nice derivation for these two theorems. So the curl of the electric field, in other words, how does it go? How does it curl? This is what this operator is, must be equal to minus, because now I lift this and I take the derivative inside, and B can potentially depend on space, which it does, then this becomes just a partial derivative of B with respect to time. So this is equivalent to Faraday-Lenz law, with the exception I have a minus in here. Let me remind you of what this operator in here is. The operator, this one, is actually taking the curl, and the operator itself is just vector whose components are the partial derivative with respect to x, with respect to y, and with respect to z, and I just use the cross product as I use it normally for anything else. Okay, we're going to deal with this one in here. So now we know how the electric field circulates. This is how it does. If there is a very magnetic field, it will circulate. How the field circulates. So the story is complete now for the electric field. We know how it circulates and we know how it flows. That's all you need. Okay. Now there is another part to the magnetic field, because we know it never flows, but we know also it circulates. So how does it circulate? We found Ampere's law. So I'm going to write it Ampere and leave a space in here for Maxwell, because he fixed it, law. And that law, there is something wrong with it as it stood, need to be fixed. So we need to fix that law first before we proceed. Okay. So let me first of all state it the way it was stated by Ampere. So it tells you that the circulation of the magnetic field over any closed path, that's what the circle means in here, is equal to mu naught times I enclosed. That's what it is. But Mr. Maxwell argued that there is a term in here that needs to be added. Mu naught times another current. Okay, so let's see why is that. Okay, let's see the argument that Mr. Maxwell presented. Because actually with these laws in here, they don't conserve the charge. Current and the charge are not conserved. So that's also, there is another argument based on the conservation of charge, that we need another current in here to fix the thing. Okay, and once Maxwell fixed that, it became known as Ampere Maxwell Law. Okay, so let's see his argument in here and why that needs to be fixed. Take a capacitor. Man, you cannot draw parallel lines in here. There has to tilt one way or the other. I have to draw it probably slower. Hold on. Or I could do this. How's that? So this is a capacitor that we know and love. Okay. Now, since I have this, why don't I draw a line in here leading to one side of the capacitor and another line in here leading to the other side of the capacitor, and imagine a point in space in here, P. So this is a point, okay? So this doesn't mean that, so a point P in space, okay? And I have a current I flowing through the circuit. In other words, I'm building a charge in here. It's already Q, but I'm piling up charge at the rate of I equals to dq over dt. We know that, okay? So in other words, I'm removing charge on the other side at the same rate, which is I equals to dq over dt. So the current is flowing in the opposite direction, the same current I. He says, okay, let me find the magnetic field at the point P using Ampere's law. Well, Ampere's law says, if you take a circulation in this case, because the current is flowing this way, so the circulation is going to be coming out according to the right-hand rule. So this point in here, the magnetic field is going to be coming out of the screen. And we know exactly how much that value need to be. It has to be a B, if I call this distance R, it has to be equal to mu naught I divided by 2 pi R. Because if I take a circle now, of radius R and go on it counterclockwise, the circulation of the magnetic field in that place in here on that circle, because B is constant, depends only on how far R is. Because it's a circle, then in this case, the circle has a constant radius, so the magnetic field is constant throughout, and the circulation is going to be just 2 pi R times this number. So the circulation in here on one side of BDL is simply going to be B, which is constant, and it's equal to mu naught I divided by 2 pi R times the circumference in this case, and the circumference is exactly 2 pi R. Cancel the 2, and the value is mu naught I. Okay, that's good. That is Ampere's law. That is what it says. The circulation of the magnetic field is equal to mu naught times the current enclosed through this surface, because I took this sphere, this circle of radius R. So there is no problem with this one in here. He said, imagine with me if this was made out of a thin material, and then we blow on it. Okay, fine, blow on it. So it's going to be at some point shaped like this. Okay, so it's no longer a circle, in other words. Obviously, Gauss's law, Ampere's law says the circulation on this side is going to be mu naught I divided by 2 pi R, because the magnetic field is the same thing in here. On this circle of radius 2 pi R, that is the value. That's not going to change. And on the other side is equal to mu naught times the I that is penetrating that surface. And it's the same I, actually. Here it is. It's the same I. So there is no problem. So multiply mu naught I, and this must be equal to the circulation in there. And since the same path is surrounding that new surface, if you wish, after you blow on it, there is no problem with this one. So it's beautifully matched in here. You know where this is headed. It's headed toward the blue screen in here. Here is where the problem is going to be. If you keep on blowing on this, it's going to be in this area in here. It looks like this. So now it's inside the capacitor. So on one side, it's the circulation. It's still 2B times 2 pi R, and B is mu naught I divided by 2 pi R times 2 pi R. On one side, for the blue screen. For the red screen, first of all, for the red one, it's still true that the other side is mu naught I. So there is no problem. The problem now is on the blue side, there is no current going through this one. There is a gap between the capacitor. So on one side, it must be 0 times mu naught, if you like. On the other side, it's mu naught I. So there is a problem now. We need to fix it. He said, okay, if you keep on blowing, I agree with you. If you keep on blowing on this thing, at some point, it's going to be here. And there is no problem with this one, because the current that is enclosed is the same I that is taking charges from the other side. And there is no problem with that. That is still works beautifully, because on one side, it's mu naught I. The current enclosed is I. On the other side is mu naught I, and the two match. There is no problem. The problem is in this area in here, the gap between them. That is a problem. That's where the problem lies. So he said, yes, there is no current in there enclosed, but there is a magnetic field in that region. There is an electric field, I'm sorry. And the electric field is equal to sigma over, that we discovered, sigma over epsilon naught. Okay? So this electric field now is equal to sigma over epsilon naught. If I multiply both sides by sigma, by epsilon naught, this is epsilon naught times E. And sigma is the amount of charge per unit area, this area in here of this thing in here. So sigma is equal to Q over A. Now, that means that epsilon times A times is equal to Q over A. from here, there is a charge actually, and that charge is equal to inside. He thought actually there was a charge, but mathematically this is true statement that this value is EA, E times A. And E times A is nothing but the flux of the electric field. It's the electric field times the current, the area. So that is the flux of the electric field. And that is time dependent because Q is changing with time because there is a current that is dumping charge on all the time. So there is a current in here that is changing this value. As a matter of fact, you can calculate this current to be I, which is dq over dt, to be simply equal to epsilon naught times the change in the flux of the electric field with respect to time. Okay? He said this is the current that needs to be added to this expression. In other words, I have to multiply it by the rate at which the flux of the electric field divided by time. Time is epsilon naught, because I need this epsilon naught in here. It's part of the problem. So mu naught times epsilon naught times the change of at which the flux is changing. Now all is going to be well if you do it this way, because this term is true 0, but this one in here, when I take mu naught times epsilon naught times the rate at which the flux of the electric field is changing with respect to time, the derivative of that. So it's going to be the derivative of the same Q that is being added in here times the divided by the area, and that is the derivative of sigma, and that is the derivative of everything else, and that's going to give me the same value, the same numerical value, if you wish, after I divide this rate by, because it's going to be dq over dt divided by epsilon naught, and when I multiply by the area and divide by the area cancels, actually, and the epsilon naught cancels the epsilon, and that is the I. So I recover this expression mu naught I if I do this algebra. So in other words, he worked his problem backward to fix it. Okay, he knew what he needs, and he worked his problem backward, taking advantage of this expression in here, I equals to dq over dt, and that is how he basically arrived into this expression. That in general, this is true. So he said, okay, in here, there is no electric field that is changing in time, so there is no flux for the electric field. So in this case, it's just mu naught I. In here, it's the same thing. Anywhere else in here is true, but in here, there is no current enclosed, but there is a changing electric field. So which means that the flux of the electric field is changing, and that is exactly what is needed to fix this expression. As a matter of fact, this is coming from this, stemming from this relationship, which is a conservation of charge. In other words, a current takes charge from a place or adds charge to another place. So this is actually equivalent statement to this one. And from here, Maxwell's equation, Ampere's equation, it became known as Ampere's Maxwell's equation. So now the picture that emerged from this expression is that this law now for Ampere needed to be corrected. And this is now how it looks like. The flux, not the flux, I'm sorry, the circulation of the magnetic field is going to be mu naught I plus mu naught epsilon naught, the rate at which the flux of the electric field is changing with time. This is not the flux of the magnetic field. The flux of the magnetic field is needed for the other one. And that put balance actually in the equations, and we have now symmetry between both of them, between Faraday-Lenz law and Ampere Maxwell's law, because of this term. As a matter of fact, I'm going to rewrite this expression symbolically in a different fashion. This is equal to mu naught times the integral of the current density times dA. And this is equal to mu naught epsilon naught, the derivative with respect to time of the integral of the electric field times dA. This is the same thing as the flux of the electric field now. And this is simply the integral of BDL. Using the same theorem as before, Stokes theorem, we can convert this one, and again, this is outside of the scope of this one, at least this class. And this will become the curl of B must be equal to mu naught J, which is the current density, plus mu naught epsilon naught, the derivative of E with respect to time. So this is how the magnetic field circulates actually. So we now have full coverage of everything. We know how the electric field diverges or flows. We know how it circulates. We know how the magnetic field flows, which it never does. And we know also how the magnetic field circulates. So we have everything we need now to find them. These equations normally are very hard to solve. So let me rewrite them now. one next to one another. So the full picture. We know that the divergence of the electric field is simply rho over epsilon naught. We know that the divergence of the magnetic field is 0. Okay, that's because there are no monopoles. We know how the electric field circulates. The electric field circulates in such a fashion that it's equal to minus the derivative of d with respect to t. This is Faraday-Lenz law. And now we know how the magnetic field actually circulates, which is mu naught mu naught j plus mu naught epsilon naught, the derivative of E with respect to time. So we have the full picture now. We're going to go to a free space, and in free space, we're going to do the following. In free space, there are no charges, rho equal to 0. And we don't have currents also, J equal to 0. So this is basically the same equation is now written in free space. And this is what we really need to solve. Now that there is no divergence for the electric field because there are no charges now. And there is no divergence for the magnetic field all the time, period, end of the story, regardless, because there are monopoles, no monopoles. And this, the circulation now of the electric field is simply equal to minus the time change of the magnetic field with respect to time. In other words, a circulating magnetic field changing with time will create an electric field that is circulating. And also a circulating or a time varying electric field will create a circulating magnetic field. So this is the big picture now. So these are the equations that we need to solve. Obviously, even in this form, which is a lot simpler than even the original form, they're very hard to solve. So what we're going to do in here, we know about polarization. So what we're going to do in here, we're going to take a polarized electric field, E in a specific direction, really. So I'm going to take E in the X direction. So run the light or the signal along specific direction. Now we have an electric field that is easier to handle. Once we do that, we're supposed to find the magnetic field and the electric field, okay? And it turns out that the solution for this equation is going to be a wave equation. This is where physics 4C is going to come in handy, because it's going to identify the solution from there for us, okay? Then I know some of you did not take physics 4C, so I'm saying things that probably you're going to see in the future, but if you took it, that's fine. You're going to recognize the equation. So, and that is chapter 17, actually, from the book. So typically, this class happened after the other one. That's why we say that. So I'm going to stop in here because we want to really go through a lot of equations to solve the equation, okay? So I don't want to, when we meet on Thursday morning at 10:30, by the way, if you guys have a free time before, we can meet before or stay longer, depending on how you guys feel about it, so that we need to finish this one. And we need to introduce some very, very important concepts. And the biggest concept we're going to introduce is the Poynting vector. And from there, we're going to find all kinds of uses for it in terms of energy, in terms of momentum, in terms of pressure, in terms of everything else. And we will be done with the concepts and we'll start doing applications. Sounds like a good plan?
Sounds like a plan.
Okay, very good. So I'm going to stop right now. Very good. So I'm going to stop recording right now.